You are.
Okay, sir. Thank you. So, hello everyone. I'm Navneet, a student coordinator of the Space Club, and today we have gathered here for the 68th webinar session, which is quite remarkable. We have been doing this for the past 4 years. We started it during the Corona pandemic in 2020, when we had this group of student fellows of the club who came together to start this venture. And ever since then, we had a lot of discussion in a broad spectrum, ranging from space science all the way to life sciences, which has been quite interesting and which has also indeed helped a lot of students to achieve their dreams and understand more about these fields. And on this 68th session, we are having an interesting topic as usual, which is star clusters, jewels in the sky. And for this talk, we have an eminent personality from the Department of Earth and Space Sciences, IIST, which is probably the only science institute in Asia which is solely devoted to the sector of space science and technology. First of all, without any delay, let me welcome you, ma'am, for this wonderful session. And we are so glad you're here with us today. And it's also worth highlighting at this moment that there was something else that we started along with the webinar series, which is the Sky Safari. And as the title suggests, Sky Safari is literally the safari of the night sky, which is currently being led by one of the most prominent science educator and astrocolumnist in Kerala, Mr. Surendran. And there we have almost on a regular basis, we are having these wonderful discussions about night sky, along with regular input of photographs from various parts of South India. So if any of you are interested in joining the venture after this session, you can contact any of the student coordinators via mail or personal contact, including myself, and we'll let you in. So let me get into the official duty. Let me welcome every one of you, our founder, Ike Kuti sir, mentors, Shajil sir, Padmanabhan sir, and all of you to this session. Also, I'd like to extend my warm welcome to every one of the participants who are here with us. I know it's exam time going on, and many of you are actually working really hard to complete your school studies and all those things. And despite that, we're having a lot of students here with us, which is indeed a thing of happiness. So without any delay, let me hand over this session to Shajil sir. Sir.
Okay, thank you, Navneet, and it's a time to start our session. Today we are sitting here on the 68th session of UL Space Club webinar sessions, and we are proud to be here. And all the students are with their examination thoughts and activities, and that's why we could see a few of them are not. We couldn't see a few of them today. Anyhow. The gathering is the interesting, so enthusiastic students and teachers and veteran scientists like Padmanabhan sir and Kuti sir, and few of them are still joining, and it's a happy moment for us. And today we have a great speaker from Indian Institute of Space Technology, Thiruvananthapuram, Dr. Sarita, which she's a professor in Department of Earth and Space Science. And she's contributing well to the student community and for the society in case of sky and space, and mostly about the stars. And she's an expert, and she's a very science propagator from that great Indian Institute of Space Technology that's constantly supporting UL Space Club for the past few years. And she's she's a PhD in physics from Tata Institute of Fundamental Research, Mumbai, and is an alumnus of Hyderabad Central University. And she has been here in IIST for the past from 2010, and she is engaged with this kind of research and publications, more than 64 publications and book chapters, and she is guiding already completed more than 6 PhDs in IIST. And she's so interested in talking to the students about the stars. Today's topic is the clusters, the jewels, star clusters, the jewels in the sky, and that would be an interesting topic. We have a Sky Safari team or activity here that's led by, that's already mentioned here, the famous our Surendran, the amateur astrocolumnist, and he's working on this area for the past 40 years, and he's working in rural areas, and he also joins with us. So anyhow, it's a great moment for our children to hear more about the sky and the stars and their secrets from a research personality from a great institute of space technology. And I welcome all the gathering and the students, veteran scientists, teachers to this forum to hear from Dr. Sarita Beach. And I thank Dr. Mahesh Hariharan, Registrar IIST Thiruvananthapuram, for introducing the scientists to this forum for us. And I welcome once again all of you, especially Surendra Puneshiri sir and our founder E.K. Kuti sir, former director ISRO. With your permission, I invite Dr. Sarita Beach for her marvelous talk. Welcome, ma'am.
Any link problem?
Hello. Am I? Hello. Am I on? I think some noise is coming, right? I think I have this issue. I will anyways try to speak earphones again. Yes or no?
Some disturbance is some disturbance.
Is it still?
I think it is slightly better now. Better.
It is slightly better. Can I? Okay. So I think I'll continue this way because I think this earphone, maybe there's some issue. So thank you again for inviting. Without too much ado, I think I will start the presentation. And in the interest of bandwidth, I think I will switch off my camera for duration of my talk because I find that in Google Meet, if there is issue, the first thing that gets affected anyway is the video. So I will share my screen. And please let me know if you are able to.
Yeah, it's coming.
Can you see the presentation?
Yes. Clear.
Yes. So I can start now, right?
Please.
Yeah. So today I'm going to talk about star clusters, and I'm glad to know that many of you are already looking at stars and constellations and so on. So I look forward to a lot of interaction and discussion at the end of the presentation. What I will be covering about is more from the astrophysics perspective. What are stars? What are the different types of stars and so on? And what are star clusters? I will also touch upon constellations. So to begin, start with stars. When you look at the night sky, you see a large number of stars in the sky. And I'm sure all of you have seen this, right? And they are also very intriguing objects. And the nearest star to us is, of course, our sun. And being so close to us, it provides us a lot of information about the stellar interiors. And in fact, physicists have developed the models of stars, how the star structure is inside and so on. So to aid, the sun has really helped a lot because it is very close to us. And it helps us understand about the models of stars and how we would like to not only understand the models in terms of the structure, but also how energy generation occurs and how it is transported to the surface and so on. So to begin with, define a star. So star is an entity which is bound by self-gravity. When you say bound by self-gravity, it automatically means it is spherical, because when you are talking about gravity, then it goes as gm square by r. In this case, the mass is the mass of the star, and r is the radius of the star. So since the parameter here is the radius, it has to be the same in all directions, and so your stars are spherical. And this there are two important conditions for the definition of a star. First is it should be spherical, that is bound by self-gravity. And second is it radiates energy from an internal source, which is mostly nuclear energy. So these are if any of these conditions are not satisfied, then you cannot call it a star. So we know many other astronomical objects, right? For example, if you think of planets, asteroids, comets, they do not satisfy one or both of these conditions. For example, if you look at planets, they are spherical, but they do not have nuclear energy production at the center by nuclear fusion reactions. But if you look at asteroids or comets, even the first condition is not satisfied. They are not even spherical. And as I mentioned earlier, our star is the sun, which can be studied in great detail and helps us understand a lot about stars. But after the sun, the nearest star is Proxima Centauri, which is 4.2 light years away. And I'm sure you know what light year means, the distance that light takes to travel in 1 year. Which means that if you are looking at Proxima Centauri now, you're basically seeing a star which was 4.2 years older. That means because the light that is coming now has started off 4.2 years ago. How the star is now, you will know only 4.2 years from now. And if I large scale, we know that stars make up our galaxy, and our galaxy is the Milky Way. And astrophysicists have statistically also calculated roughly how much. You won't know exact number because we cannot sit and count each individual star. But what we do is we use statistical processes to get an estimate of the number of stars in the Milky Way, and that is of the order of 100 to 400 billion stars in the Milky Way. So just imagine the magnitude of stars that we have in our galaxy. And this is just one galaxy, and in the universe there are around again 100 billion galaxies. So if you have 100 billion galaxies, if you assume on an average that each one of them has, if you assume they are not all same, as 100 billion stars, then the number of stars in the universe is astounding, of the order of 10 power 20 or so. Now, what are stars made up of? Okay, so if you stars were researched upon and people were trying to find out about stars, they initially thought that this, like Eddington and so on, they used to think that stars also were like Earth. You had a lot of iron and you had a lot of silicon and so on, silicon dioxide and so on. And that is why it was very surprising when they did spectroscopy and they found from the spectra of stars that it is not made up of mostly silica, but it's rather made up of mostly hydrogen. So you see the composition of the universe is something which you see on the right side, which mostly around 72% or is made up of hydrogen, 70% is hydrogen, around 28% is helium, and then you have the other heavier element in 2%. Okay, so all the elements, just to introduce you to the astronomy jargon, in astronomy, every element hydrogen and helium are called metals, even though oxygen, carbon in standard terminology is not a metal, but for astronomers, everything other than hydrogen and helium are called heavy elements and they are called metals. And although they may also be in gaseous phase. So it's not the normal definition of metals which we generally use in physics or science. In astronomy, it's slightly different definition. If you see the composition of Earth here, then you can see that it is very different from what you see in the universe. And if you see the life composition, again, this is very different. So people are also trying to probe what could have led to this kind of composition, because the universe, or most, when I say universe, most of the stars are, in fact, all the stars have similar composition, which is something like this, 70% hydrogen and most of it helium and very little heavier elements. Whereas when you see the Earth, it is very different. If you see life itself, then again you see it's mostly carbon, oxygen and hydrogen, and then you have phosphorus and so on. So this is also a puzzle that we have to solve eventually. So if you look at the star, I mentioned that hydrogen is around 70. If you say parts per 10,000, then it is 7,500 parts. Then helium is 23 parts. Oxygen is 100 out of 100,000 and so on. This is to tell you that in stars, you do have these other elements also. Oxygen, carbon, neon, iron, nitrogen, silicon, magnesium, sulfur, argon. So these have been found. How do we know that these elements exist? Because the light which is coming from the surface of the stars, you analyze that light, and from that, that is called the spectrum. When you are taking the light and analyzing it across the wavelength, that's the spectrum. You look at the spectrum, and from that you can gather, physicists can gather which elements are present on the surface of the star. And we have found traces of all these elements, indicating that all these elements are present in some amount in stars. But majority of it is mostly hydrogen and then helium. Now, what is the cause of energy generation in stars? So the energy generation in stars, as I mentioned earlier, is nuclear fusion reaction. Now, which reaction is this? As I've already mentioned just now, it is mostly hydrogen. So hydrogen, fusion of hydrogen nuclei to helium nucleus. We should not confuse between atoms here. It's not fusion of atoms, because this is a nuclear reaction. It's the fusion of the nuclei. So these kind of reactions take place at very high temperatures, because since the hydrogen nucleus is a proton, right? And if you want to fuse two protons, then they are both positively charged, and if you bring them together, they will repel. So you need very high temperature so that they get very high velocities, and because of these high velocities, they can overcome the repulsion and approach each other. When we approach very close to each other, then fusion process can take place. So this is how nuclear fusion reaction begins. It starts with, now one would think that, okay, does two hydrogen nuclei fuse to one helium nucleus? No, because hydrogen nucleus comprises of one proton, helium nucleus comprises of 4 particles, which is 2 protons and 2 neutrons. So obviously from 2 hydrogen nuclei with protons, you cannot make a helium nucleus, right? You need at least 4 of them. And that is what is shown in the reaction here. You have 2 hydrogen nuclei coming and forming deuterium here, and then this deuterium forms helium 3-2. Okay, helium 3-2 in the sense there is only 1 neutron and 2 protons, and then one more proton comes and interacts, and another deuterium nucleus, one more to form the helium 3, and 2 such helium 3 combine to form helium 4 nucleus, that is 2 protons and 2 neutrons, and it gives off 2 protons. Now you would say that it has given off 2 protons, but we started off with 2 protons, right? But there is also another helium 3 nucleus which is used up. So if you actually count the number of hydrogen nuclei that have gone into this reaction, it is 3 here and 3 for this. So that is 6. And 2 are given off. 6 minus 2 is 4. So 4 particles are used up, or protons are used up to make a helium nucleus. In the process, it gives off a lot of energy. And that energy is what we see from the stars. Because this energy is given off and these reactions occur in the core of the stars, in the center of the stars. In the case of the sun, the temperature of the center is of the order of 15 million Kelvin. And the pressure is also very high, of the order of 10 power 28 pascals or so. So these high energy generation, it passes through the entire different layers and comes out through the surface. So the energy transfer that happens from the center to the surface defines the structure of the star, defines how the star is going to be. So at the center, the temperature is of the order of 15 million Kelvin, but the most nuclear energy generation happens only when very temperatures are high. But the temperature by the time it comes to the surface is less, because the outer layers are not involved in nuclear energy generation. So the stars which are actually fusing hydrogen to helium, in astronomy we call them main sequence stars. So the sun is also a main sequence star. Now this is the longest stage in the life of a star, where hydrogen fuses to helium in the core and releases energy. And over this phase, when the star is in the main sequence phase, its size does not change much. And because we are seeing the sun every day, right? Science we don't see. And in fact, in the entire life cycle of the star, for as long as it lasts, this phase is the longest phase, the main sequence phase, where it is fusing hydrogen to helium in the core. Now you will wonder, are there other kinds of stars? Yes, there are other kinds of stars which are non-fusing hydrogen to helium in the core, and I will be talking a little bit about them. So the luminosity is the energy which is given out per unit time and by the star, and it does not change much across the main sequence phase. So to give you an example, the sun is a main sequence star, and its lifetime we can calculate is of the order of 10 billion years. So we needn't worry. But the question is, where are we in the life right now? In the entire time of the star, we are roughly halfway through. The age of the sun and solar system is roughly 4.5 billion years. So we still have another 4.5 billion years for the main sequence phase of the sun to last, which is quite a long time. So we needn't worry about what is going to happen and is something going to happen to the sun and so on. Because very often I have heard these, have had these queries from children, which is very valid because they would not know as much. Like I said, the size doesn't change much. Why doesn't the size change much? If we look, I've just said, right, that in the center you have the energy generation which is occurring due to nuclear reaction. So once this, and this energy is a lot. So this energy, once it is given out, what would you expect if there is a gas around it? Because we know that the star is mostly made up of plasma, which is very ionized gas and so on. So if you give a lot of energy to this plasma or any gas like this, gaseous medium like this, then what would happen? You would expect it to expand, right? Because you are giving it a lot of this energy. But what happens is and if that were the case, then the sun should be exploding, right? Becoming bigger in size, because every time you just generate this energy, then how come its size is maintained constant? And that is because of the self-gravity. So the size of the stars does not change much in the main sequence phase, at least, because whatever energy generation is happening, that is balanced by the self-gravity of the entire star. So these two are balancing each other, as a result of which the size is not changing much. So this is a constant tussle which is happening between gravity and thermal pressure. If, for example, it goes out of this equilibrium, for example, thermal pressure suddenly becomes very large, then it will explode. And if self-gravity becomes, if for some reason the nuclear energy generation stops, what would you expect? You would expect that self-gravity will take over and it will begin to collapse, which is what happens when in the core the hydrogen is completed, that all hydrogen is fused to helium, and outside of you may have hydrogen, but the temperature is not enough for it to start a nuclear fusion reaction. So now what happens? Now there is no more hydrogen, no more fusion. So self-gravity will take over and it begins the collapse phase and so on. So I'll come to that aspect in a while. Trying to understand stars and study stars, what they did was, which is in the beginning of 20th century, they took the spectra of a large number of stars. When you take spectra of a large number of stars, that means they're taking the light from the stars and dispersing it with a prism or a grating and so on, and seeing if you are seeing any absorption lines, emission lines, and so on. If you're familiar with these concepts, fine. If you're not familiar also, it's okay. So then these are called transitions. They could find out what is the composition of the stars, and based on the strength of these lines, they could classify stars based on surface temperature, because ultimately the radiation seeing and that which we are using for classification is coming from the surface of the stars. So based on this radiation that is coming, the stars are classified into several spectral classes. Okay, so which is shown in the figure below. So the O-type stars are the most massive and biggest stars whose surface temperature is of the order of 60,000 Kelvin. Okay, now at the center the temperature would be much higher, but we are only looking at surface, and it is also much larger in size. These are the most massive stars that we see in our universe. And then you have the B-type stars. So these are whitish in color, these are bluish in color, and so on. These are also bluish, whitish, and so on. You can't really segregate because it's not just one color that these stars are giving out. They are giving out a range of wavelengths, and therefore you cannot pinpoint exactly, that you are seeing blue star, you are seeing green star, you are seeing purple star, and so on. You see mostly reddish colors, and that is also related to how our eye perceives these stars. So you see roughly whitish stars, bluish stars, yellowish stars, maybe orange stars, and reddish stars. So the most massive stars would appear bluish whitish, and after that you have the A spectrum. So these are called spectral classes. You have the A type stars, you have the F, G, K, and M. Now these are alphabets which are given to these different spectral classes. Now, although this is one spectral class, between this and this there are different types of stars, because it is a continuous distribution. You may have slightly smaller but bigger than this B. So there are subclasses also. So O1, O0, O2, and so on. And you can have B0, B1, B2 till B9. And in this way, astronomers classify stars. By looking at the radiation coming from stars, they can tell its surface temperature. And once you know its surface temperature, you can classify these stars into O type, B type, A type, and so on. Now the sun is a G-type star because the surface temperature of the sun is 5,800 Kelvin. And as I said, it starts from 60,000 Kelvin and reaches M-type stars are the most coolest and reddish stars. They have a surface temperature of the order of 3,500 Kelvin. Now, these are some of the properties of the stars. For example, of course, here the size is not shown, only the colors are shown. So you should not think that all of them are at the same size. The size is definitely much larger for O-type and gradually decreases for the M-type star. But this table gives an estimate of the range of temperatures and what compositions or lines you see on the surface. So the temperature is in the range of around 30,000 to 50,000 for O-type stars, and it comprises of ionized helium, because once you have such high temperature on the surface, even helium begins to get ionized. Then you have the B-type stars with surface temperature 10,000 to 30,000, and these show helium and some amount of hydrogen. Then you have the A-type stars which show strong hydrogen and some metal lines, and so on. So these are the features which are seen on the surfaces of these stars, and this is the temperature. So as I already mentioned, the sun is a G-type star. It appears yellowish like this, and its surface temperature is of the order of 5,800 Kelvin, which well fits into the G-type. In fact, the subclass is 2, so it's a G2 type star. Now, this night sky, which I'm sure all of you have done, then you must have seen this. Some stars appear bluish, some stars appear reddish, some stars appear, and that I already mentioned some time ago. The different types of stars appear to have different colors. Now, these different colors are related to the surface temperature of the stars. The hottest stars will be the bluish, and then you have the whitish and so on, as already shown here. And then when you go to G-type, it's yellow, and you have orangish and reddish. So if you look at the stars, looking at the stars itself, you can gauge that these are related stars as compared to the blue type stars. But when I say cooler stars, they are not as cold as ice, and as you can see, it's just a relative term which I am using with respect to the most massive stars. So the coolest stars would have temperatures of the order of 3,500 Kelvin on the surface. So we are generally characterized, when we talk about stars and their classification, it is on the basis of the surface temperature of the star, which is ranges between 60,000 and 3,500. Now, life of a star. Is a star always like this? How did it start burning hydrogen to helium? What will happen afterwards? So I will talk briefly about this. So if you look at this picture, you can see one very famous constellation, at least over Kerala, we see this very, very nicely. This is the Orion constellation. Now we wonder, and here you can also see the M42 nebula. I don't know if you can see my cursor, but this nebula is here. This is known as the M42. This is a region where stars are forming, and this can be seen very nicely with a telescope actually. Even with naked eye, you may just about see something, but with the telescope or binoculars, this can be seen very nicely. Now, if you look at the stars and wonder what is there between the stars, is it just empty space or is there something in between? It so happens that the space between stars is not empty. It is made up of very low density medium, mostly gas, and little bit of dust. That is known as the interstellar medium. So the gas component is, as discussed, the 75% of the gas component, or 70% to 75 is hydrogen, then you have helium and heavy element. But 1% of the interstellar medium is interstellar dust. Interstellar dust is very fine particles, mostly made of silica, and it could come from ices and so on. They are not as big as the dust particles we see on Earth. They are very fine. And there are people who are doing research only on trying to understand more about this interstellar dust. But I'll not be going into that in detail for now. The question is, why should we study interstellar medium at all? Because this is the medium from which stars form. So why are we talking about this? Because this is the medium from which stars form. This is the medium in which stars eject matter after they finish their life cycle. And most importantly, all bodies, planets, and everything is made from the interstellar medium. And you can also start worrying or not worrying or thinking deeply. Come from? What are we made up of? When did we come about? What is the material we are made of? It so happens that all that we see around us, which is not a star, is coming from interstellar medium. And that is what brings me to the elements origin. We see a lot of elements around us, right? In the Earth, you can see, and you have seen this periodic table n number of times. But have you ever wondered where did they come from? And that is literally, I mean, where on Earth did they come from? And it so happens that all these elements are synthesized in the interiors of stars, and with certain processes they are turned into interstellar medium, and when and other things form, they are formed from this interstellar medium. So this interstellar medium is mixed with all these heavy elements. And in fact, astrophysicists have worked together to find out which element has come from which process, stellar process. And that is what this periodic table tells us. For example, the yellow ones show that it is a merging neutron star gives rise to that element. Okay, you can take your favorite element and try to see where this element has come from. Or it could be exploding massive stars, exploding white dwarf stars, and so on, or Big Bang itself. So different elements have come from different processes, and that is why this particular periodic table is very interesting, because it has a lot of information based on the outcome of a lot of research by astrophysicists to help us and inform us that what is the origin of these elements that we are seeing. And so everything is made of stardust, because we are also made up of these heavy elements which have been processed in the interiors of stars. Now, how do stars form? They form from the interstellar medium, and interstellar medium consists of this the dense phase and not so dense phase. So when the interstellar medium is very dense, then it is called a clump or a core, and within the clump or core, gravitation can take over and it can start collapsing. And once it collapses, these are the various phases which leads to the formation of stars. Once it starts collapsing, then initially there is some bit of rotation. Because there is some bit of this rotation, it tends to flatten out and you form a disk. Because initially rotating this and it is compressing, then because of conservation of angular momentum, it will start rotating very fast. And anything that rotates fast tends to flatten. We know this also from the case of the Earth, because Earth is not a perfect sphere. It is bulging at the equatorial plane. This is because of rotation of Earth. Similarly, if you have some very less dense material and you rotate it very fast, it tends to flatten. So what you see here is this very high density protostellar which is going to form the star, and around that you have the formation of a disk, and there is material which is coming in or accreting or the collapsing onto this star, the protostar. At the same time, some material is also given out in the form of jets. I will not go into those details. But what I would like to mention here is that at the center of this protostar, when the temperature becomes very high, density becomes very high, then nuclear burning can get initiated. Hydrogen fuses and leads to the formation of a star. But what happens to the disk around it? In the disk around it, you have is the region where planets are found. That is why you must have observed that most of the planets around the sun, they all lie in one plane. They are and this is because they are formed from the disk around the star itself. Let's look at what happens. So this is how a star is formed. So once a star is formed and it starts stably burning hydrogen to helium in the core, that's known as the main sequence phase. And this main sequence phase lasts for a very long time. But then what happens after that? After that, this is an average star, this is a massive star. Average star is a star like sun. Massive star means star which is more than 10 times mass of sun. The evolution of the star is in the very quickly. I won't go into details because of lack of time. So this passes through a phase known as a red giant, the sun. So what you are seeing here is what the sun will be like in future. After it finishes the main sequence phase, it will become a red giant, which is size will become much larger and it will become redder. And at the late stage, what is left of the core will become a white dwarf, and all this outer material will be thrown out in the form of a planetary nebulae. Over time, this material will also dissipate and with the interstellar medium, and what will be left behind is just a white dwarf. So white dwarf is a different kind of material, different kind of object, cosmic object in which no nuclear fusion is happening. It is in fact has some quantum mechanical properties. Okay, and nuclear fusion, and as a result, but it is very hot because of the nuclear fusion reaction which are occurring. So with time, the white dwarf is only going to become slowly cold and so on, but there is no nuclear fusion reaction going to occur. So this is the end stage of the stars like sun and lower mass stars. But if you take massive stars, then it leads to the formation of a red supergiant. And if in the further evolutionary stage, the outer layers of the supergiant are thrown out in an explosive event which is known as the supernova. And at the core of massive stars do not form white dwarf. They can either form a neutron star that is made up of neutrons, or it can form a stellar mass black hole. So this is one way that stellar mass black holes can form. So this is about the evolution of stars. Now I go on to constellations and star clusters. So constellations, I'm sure you must have seen a lot of constellations in the sky. They are the patterns that we see in the sky. And in fact, International Astronomical Union has divided the sky into 88 zones associated with these constellations. But what I want to emphasize here, and which we are associating these constellations with certain mythological figures, and different cultures will have their own figures associated with the constellations. Some may be similar, some may not be similar, and so on. So these are constellations refers to the patterns of the brightest stars in the sky, and they appear to form certain shapes and so on. So this, of course, again, I bring back to our constellation. And here what we do is when I draw these lines, these are imaginary lines trying to say like, okay, this looks like a hunter and so on. Okay, the belt of the hunter is the 3 stars, which is a very characteristic shape. Then you have this sword hanging, and it leads to the M42 nebula and so on. But what I'm saying is that the stars of a constellation, they only appear form a pattern in the sky, but they are not physically related to each other in the sky. It is just a pattern. Usually, this is just the projection effect. So the stars of a constellation may be located at very different distances from us. Okay, so this is this figure on the left hand side shows that if you are seeing seeing stars in a certain constellation or in a certain pattern, for example, this is the Big Dipper, if you take, then you see that they are actually very different distances. But since they are all very far from us, it appears to be projected on a dome-like sky, right, celestial sphere, and then it appears like they are appears to have certain shape. But in reality, they are all at very different. The stars stars of constellation are at very different distances from us. So this is also evident from this figure which is shown on the right. It's a schematic figure that you have these light bulbs which are arranged in a kind of different distances, but if you had to project them, then it would appear like Orion. But in reality, all the stars of these constellations are at different distances from us. So these constellations are just out of curiosity or interest and to identify certain region of the sky, at least for astronomers. But for us, what is of more interest are something known as the star clusters. Okay, but before I go into that, I had this other figure also, which shows that you may be familiar with some of these stars, the Betelgeuse, the Orion Nebula, and various stars, the Bellatrix, and so on. Yeah, so I come to this next aspect, which is the star cluster. So what is a star cluster and how does it differ from a constellation? So star cluster is a higher density group of stars which we can identify in a region of the sky. But the most important thing is the siblings, the stars in a cluster. They are formed from the same molecular cloud, okay, and formed at around approximately the same time. And in the beginning, they are actually bound because they formed from the same cloud of interstellar material. Okay, it may be strong or loose. Over time, this cluster evolves, the gravitational binding reduces, and then they can move away from each other. But when you see a cluster of stars in the sky, this tells us that this is a group of stars which formed at around the same time, and if you study these clusters of stars, it can tell us how star formation is occurring, what are the processes leading to the formation of these stars and clusters. So they threw a lot of light on the star formation process itself. Clusters are broadly categorized into two types. One is the open cluster, the other is the globular cluster. So the open clusters consist of hundreds to thousands stars. They are rich in heavy elements or metals, as I already mentioned to you. They are found in the disk of the Milky Way. When I say young, from our time scale, that's much older, but from the time scale of the age of the universe, which is around 13.6 billion years, they are young in the sense that they are a few million years or a few billion years only. They are also associated interstellar because they are young and interstellar medium lingering around them. Now, if you look at the other cluster, which is the globular cluster, this is a very different kind of entity. It comprises of thousands to millions of stars, which are spherical in shape. They have a wide range of metallicity, the stars in the globular cluster, and they are found not only in the disk but also in the halo of the Milky Way. And these are some of the old, unlike the clusters, these are some of the very old objects, in fact the oldest objects in the Milky Way, and which means they are at least more than 10 or 11 billion years old. So if you are wondering what is Milky Way and so on, I have just shown a picture here to tell you what the Milky Way looks like. If you see the Milky Way from top, if we could see, this is what we think it would look like, where you have the center and then you have the various spiral arms, because Milky Way is a spiral galaxy. And if you want to look at from the side, this is what it would appear like, because this is a flattened structure. So this is known as the disk and this is known as the halo. There is also some material, gas, dust, very low density. In the disk, the gas density and stellar density is very high, but in the halo of the Milky Way, it is very less. Okay, and the open clusters are found mostly in the disk of the Milky Way, whereas globular clusters, they are found in the disk, but many of them are also found in the halo of the Milky Way. I'll just show you some examples of some exotic star clusters. This is a superstar clusters. This is a very massive open cluster, which is not in our galaxy, but in our satellite galaxy called the Large Magellanic Cloud. This Large Magellanic Cloud we can't see from northern hemisphere, but if one goes to southern hemisphere, say Australia and so on, and look up at the night sky, then you will be seeing these two satellite galaxies very prominently. That's why initially they were thought that they are clouds in our galaxy, but they are actually irregular satellite galaxies called Large Magellanic Cloud and Small Magellanic Cloud. And these, for some reason, the clusters in this Large Magellanic Cloud are really much larger. The stars are also very massive, more than 100 times mass of Sun, and you have many such stars together. So there must have been some interactions on the galactic scales to give rise to the formation of such stars of such large masses. So if you actually looked at the sky from the southern hemisphere, then this is how the Large Magellanic Cloud would appear. This is the Small Magellanic Cloud, and this is the Milky Way. But we can't see it from here, of course, because this is very close to the South Pole, celestial south. Then near the center of the Milky Way, we find some very interesting clusters, because the center of the Milky Way hosts a supermassive black hole whose mass is of the order of 3.6 million solar masses. So here also because the environment here is very violent, so different kind of the environment near supermassive black hole is different from the environment away from it, and that leads to the formation or collapse of molecular clouds, leading to the formation of very massive clusters. Okay, so these are some of the clusters which are found near the center of the Milky Way. This is the Arches cluster, and this is the quintuplet cluster. This will kind of now wind up and mention that we have, I didn't want to bring in any research aspect, but I couldn't resist this because I have been working on open clusters and globular clusters and so on. And with our own AstroSat mission, we actually found one new population of stars, because AstroSat does not work in optical, but it works in one of the instruments on AstroSat. AstroSat has multiple instruments, in mostly working in UV and X-rays. There are also optical, but mostly for guiding. So we have instrument, and with this instrument we have been observing many different types of globular clusters, because open clusters, if you want to see, there's a problem, it will be too bright for the UV instrument. So in fact, one of these very massive globular clusters called NGC 2808 we had actually observed, and we had for the first time detected a new population of stars, a new type of stars. I will just leave it at that, because to understand that it requires quite some bit of understanding how these stars are different from others and so on. What are these type of stars? But let me just put it that way, that we found this very nice new population of UV stars for the first time using our own AstroSat, which was launched by ISRO and is still working. So with this, I will come to the end and summarize by saying stars are spherical objects held together by gravity and produces energy in the interior, mostly by nuclear fusion. So the types of stars are based on spectra, their spectral classification. One can also distinguish them from colors and this classification is done on the basis of the surface temperature. Then I talked about the evolution of stars, that you have stars which evolve from the main sequence to other phases. And finally, I talked about constellations and clusters. And again, among the clusters, there are two broad categories: open clusters and globular clusters. Now, if you are interested in knowing more about stars, actually during COVID time itself, there were a series of lectures which I had taken, and in fact at that point of time, with the help of Breakthrough Science Society, we had actually also conducted lots of exams and tests and so on, and given some certificates for those who completed. And the eligibility or the prerequisite was not much. High school physics, if you have cleared the 12th class physics and maths, if you know that much, then you can. Even if you don't, if you have not completed but want to learn stuff, then also they were encouraged. So we had this course which is now all available on YouTube, and if you are interested, you can go and check it out. There are a series of 8 lectures, each of 2 hours each, and this is all about stars alone. I talked a very little bit today just to give you a flavor, but if you are interested and would like to learn more in detail, because that is what we teach our students. So in the same way, there are these lectures that I have put up, and if you are interested, then the title you can give in YouTube for search is Basic Course in Astronomy, Introduction to Stars. It has 8 lectures of 2 hours each. So with this, I will come to the end, and thank you very much for this opportunity.
Thank you. Thank you, Sajal Marsh. And we had an excellent presentation, articulation by Professor Sarita Vij, who has made the presentation loud and clear. Lack of time only has made her to be little speedy, but our students are able to follow, I think, the whole thing. She explained it very well, very well, and also offered further materials for study and further interest, pursue the further interest and things like that. So what I see is, here, we have got the least number of participants in this webinar. Of course, the reason is not far to seek. We know most of the students are busy with their examination, but yet I find the students who are present here, like Hana Shireen, Rifa Fatima, Adil Prajesh, Nandana Pola, Adi Dev, they are all really keen on this subject. Of course, your focus is more on astrophysics, but the students are also looking towards that. But we have our Sky Safari, which is opening up the sky for them to learn a lot of things about the cluster. So the cluster topic is open to them for the first time. We have never had a topic of this type for quenching the interest of or quenching the thirst of students to know more about stars. So thank you very much, madam, for providing this occasion. And yourself and your institution, IIST, it has been a source of strength for us. Its founding director itself, Dr. B.N. Suresh, has addressed our students more than once, and we have met him in Trivandrum also. And your faculty like Professor Kurivila, YVN Krishnamurthy, Dr. Srija Lakshmi, Anand Narayan, they are all have been supporting us in a great deal. So thank you very much for you coming for the first time. We will look forward for a lot of support and help from you in the coming weeks and months. Thank you very much for finding time and giving an exceptionally good talk. Thank you very much.
Thank you for your kind words. I'm happy to support in whatever way I can.
Any?
Yes, it's a very informative session that we had today. And of course, the stars and galaxies are always mysterious to us, and also create more curiosity in the mind of the children. So this is too distant from us, but always when we read about Carl Sagan's galaxy, that books and all, we are always more and more encouraged or inspired to learn more about it. Even those people who have passed the student age and working, so many people can still get inspired by the stories of the stars and galaxies. So it is a very interesting program, and also the effort taken to have a regular weekly program where you deal with different topics and having good students to attend. So that is a very, I would say, it's a remarkable achievement for this, for all of you who are involved in this. And I know Shajil, I've been personally in touch with him also. So it's a great effort, and I thank you for inviting me for all the sessions, and I've attended most of them and got so many insights. So thank you again.
Hello, sir. Good evening, all. It's time to start our Q&A session. So if you have further doubts, you can post in the chat box along with your name and class. So, ma'am, I'm going the first question. What challenges? Okay. What challenges and mysteries still remain in the study of celestial clusters, and how is your research addressing them?
Challenges left. What is still very little. And people say sky is the limit. I think sky is the lower limit. That is also something that is well known. In the sense that what we know is just a little bit part. There is still a lot of physics to be uncovered. There is all the processes that I talked about, the star formation process, star evolution process, everything we know details. So to know lot of active work that is going on. Now, my area of research is mostly about how stars form. Okay, so that's why I study star clusters. And in particular, I'm interested in the study of massive stars because according to what we know about massive stars, they are formed initially when they are formed itself in the center nuclear can get ignited and energy should get released. Now, once this energy is being released, the matter that is infalling should get halted because this energy is in the opposite direction, and therefore we should not have massive stars itself. So according to our paradigm in astrophysics, massive stars should not exist in nature. But the fact that we are seeing them, somehow the process is going through and we are still form massive stars. So one of my areas of research is to study massive stars and how they are forming different phases in the earlier stages. Then I'm studying open clusters, trying to understand how the molecular cloud fragmented and led to formation of the stars in a cluster. Then I'm also studying global clusters, which I already mentioned. In global cluster, we can study the evolution of stars very well. Okay, in fact, that is a laboratory for studying stellar evolution. How? Because that is a very old stellar system, and so stars will have evolved later phases. So that laboratory provides good insights about how stars are evolving beyond the main sequence phase. So that is also my interest. So I hope to some extent this has answered what you had in mind.
Yes, ma'am. So the next question is from Suryajit. If multiple stars are produced at the same time and placed in the clusters, isn't there a possibility of some of the closest ones getting into a collision?
Although they appear very close to us, they are not very close. In the sense that if you want to have a collision, they have to come really very close to each other. And that is the star, when they are forming, they are clumps which are slightly apart. In the sense they appear very close, but they're not really that close. They are gravitationally interacting. The chance of direct collision is very little because stars also have some kind of motion, rotational motion around the center known as, which I can talk of in terms of angular momentum. That angular momentum of these stars means they are constantly moving something else, or they are binary stars and so on. That stops them from directly colliding. So there are very few cases of direct collisions, but in when the stellar density is believed that collisions could have happen and led to the formation of certain exotic stars. Okay, so these exotic stars are called, or these unusual stars are called straggler stars. So I'll not go into details, but there are some theories which say that these stars could have been formed from collisions, but you need very high stellar densities for that to happen. But in open clusters, there is the probability is very small.
Okay, ma'am. So the next question is from Archit Iyer. Why the main sequence stars with less temperature are so small, like Proxima Centauri?
Because mass. So since they are mass, they are smaller in size, in the sense that if you want to have a large mass star form, it also gives off a lot of energy. This lot of energy, when it gives out, the size of the star, as I've already mentioned, is balanced by gravity and the energy which is given out. And it so happens that this balance occurs, that more the energy given out, more will be the size of the star. That balance is the size of the star is decided by that balance. Okay, and how the energy is transferred from the center to the surface. So there are energy transfer, and those need to be considered when you are finding out the size of the star. So for main sequence stars, it is like this, but in the case of white dwarf stars, it's opposite. The more massive stars are smaller, and the lower stars are larger. So there again, it depends on what it is composed of and what are the interior processes in the center of the star. So many factors go into deciding the size of the star vis-a-vis the temperature and so on. But since we are talking about main sequence stars, I will just say it is the combined effect of self-gravity and the thermal pressure that is deciding the size of the star.
Okay, ma'am. So the next question is from Adidev. He's studying in 7th. Are all black holes formed from dead stars? If yes, how big must a star have been to form a supermassive black hole?
That's a very good question, I would say. So the black holes actually, people have found that they come in multiple varieties. So one is the stellar mass black holes, which I talked about today. They are the remnants or the collapse of the stars, leading to formation of stellar mass black holes. But these black holes of these type of black holes can have mass only up to 60 times the mass of the sun, 50, 60. That has been observed using gravitational waves and so on. But if you want to talk about some category of black holes called intermediate mass black holes, I will not talk about that because right now we are not talking about that. The question is more about stellar mass black holes versus supermassive black holes. The supermassive black holes, which are found at the center of the galaxy, they have masses of the order of 100,000s to millions to billion solar masses. These supermassive black holes are not formed in the same way as stellar mass black holes, although we don't know the reason. But what we know is that, what we know, I will tell you, is that these, first and foremost, these supermassive black holes are found at the centers of galaxies, whether it's elliptical galaxies, Milky Way galaxy, and many galaxies have these supermassive black holes at the center with millions or billions of solar mass. Now, it is believed that the formation mechanism of these supermassive black holes is different from the stellar mass black holes because these first are formed in the big when the galaxy itself was forming. So it is now what led to the formation of this, whether it was a stellar mass category or whether it was a bigger something else which was at the center of the galaxy that led to the formation of supermassive black hole, there is still a lot of debate going on. And there is a lot of active research in trying to understand what kind of objects must have collapsed in that early stage to have formed the black hole. It has evolved over many billion years to what we are seeing as supermassive black holes today. So the answer is we don't know. So we cannot say with certainty in the same way the stellar mass black holes form at least in the way that I explained. Because what I explained is about the current star formation. And star formation in the early universe is believed to have been very different because there were hardly any metals. There was only hydrogen, very little helium and so on. So presence of metals has increased over time because these are generated or synthesized in the centers of stars. So in the early universe, there would have been very little metals and therefore therefore the kind of stars that formed and the way they evolved, we believe that they would have been very different from what we see today.
Okay, ma'am. So the next question is from Adil Prajesh. Is Sun's atmospheric temperature higher than Sun's surface temperature, and what is the reason for it?
Yes, so I did aspects of the sun. I think one lecture can be dedicated only to understanding about the sun or telling some bit about the sun. So the surface of the sun, what we are calling, what I am talking about 5,800 is something called the photosphere. Beyond that, the density of the sun falls off, but the temperature profile one can get, and it so happens the temperature profile, it falls off and then increases dramatically. In the chromosphere, it is believed that the temperature can reach of the order of million Kelvin. Now, what gives rise to this million degree Kelvin? First is, how do we know its temperature? So that also is something which we need to understand. We usually estimate temperature from average kindling energy of the particles. It's not something you cannot take a thermometer and go and measure gas which is very less dense. You have to use very different kind of methods there. Okay, so we use the average kinetic energy per particle, we calculate, and then based on that try to estimate the temperature of the chromosphere. And it is believed the reason for this high temperature is not very well known, that the people are trying to probe, and I think that is also one of the reasons for ISRO to try to send up Aditya L1, because we want to answer a lot of questions why the temperature is so high, million degrees centigrade. But there are various theories about certain acoustic waves and so on, which are leading to these high temperatures, but I will not go into those details for now.
Okay, ma'am. So the next question is from Albin. How does gravitational lensing affect the apparent brightness and size of a star cluster?
Okay, when you're saying gravitational lensing, I don't know if everybody here is familiar with this, but gravitational lensing is a phenomenon where you have a certain, it's like a lens, you have a source of light, a lens, and then you have an image formation. So here the source of light could be maybe a cluster, maybe a quasar, maybe something else, and then you have some large matter object sitting in the path. Usually that is, what do you say, either a star, and usually for stars you don't see, but gravitational lensing has been observed extensively for dark matter related objects, and so the light from the background object gets lensed, and you would see something depending on the distribution of the matter which is acting as a lens, you would see the shape, you would see the image formation. The reason why I don't want to go into this is because to understand gravitational lensing, we need to understand the space-time warping. Okay, and space-time warping involves chemical theory of relativity. So since I have not talked at all about it, I mean, I can talk, but it will be too brief for us to be able to understand all aspects of gravitational lensing. So I don't really know what exactly is asked in that sense. Whether you would see gravitational lensing of clusters, we have not seen as much in our Milky Way. This much I can mention. This is usually seen for other galaxies. And for very distant galaxies in a mass when it is very, very large. But for clusters, till now we have not seen a lot of gravitational lensing. That's what I will say.
Okay, ma'am. So the next question is, how do gravitational interactions within clusters influence the dynamics and stability of celestial system, and what implications does this have for our understanding of the universe?
So we think that stars interact with each other, and because it is believed that initial phases, and now we are also trying to do research to find out, it leads to because of this gravitational interaction among stars in the clusters, it leads to the formation of many binary star systems, triple star systems, multiple star systems, and so on. So these each other and do affect the way the cluster evolves with the time. But observationally, unfortunately, we cannot see the evolution of one cluster, how it is forming to the present state, because that will involve many years, and we do not have that much time. We as astronomers use the sky as our laboratory, in the sense that we will see clusters at different evolutionary stages, and therefore from that try to gather. Okay, it's like going to a planet. You have just I'll just give you an analogy. You're going to a planet and you see a lot of aliens there, and you come back, and then you have to take a look at what you saw. So you saw these different aliens. So you saw different sizes of aliens, maybe, and then you will describe those aliens, and then you will try to read how the evolution of aliens happened, because maybe you saw a small alien, maybe you saw a big alien, and so on. And then you say, okay, based on what we know, that the small alien evolves towards the bigger alien. It may be rather not, but that's what we think based on what we know. So that's how the theory is constructed. So similarly, for what we're talking about in astronomy, we have these theories. What we do is we see different snapshots of stellar clusters, and we try to build up upon that as to how star formation is happening, how the cluster is evolving, what is the probable dynamics, plus the physics. Based on the physics we know, we include that and then try to make the theory more stronger.
Okay, ma'am. So the next question is from Hannah Shirin. She is studying 11th grade. Open clusters are typically younger stars than globulars, which consist of older stars. What happens to the stars of open clusters if they enters their end stage of life? Will it turn to a globular star, globular cluster?
So it so happens that most of the stars in the open clusters, since they are formed in the Milky Way, there is a lot of galactic dynamics. Galaxy, also other stars, since they are interacting with each other, and there are other stars in the disk of the Milky Way. So they are interacting with all these. Over time, the bonds between these stars, the gravitational attraction and so on, are such that these stars slowly kind of loosen with time, and they become some what we call field stars. They are no longer gravitationally bound to each other. Okay, that is what we expect. For the sun, we see it is an isolated star, but when it was formed, it would have been part of some cluster, but no longer it is so. Okay, so it means that over the time, they will be from each other and become some kind of isolated entities, but they could still be binary systems, triple systems, and so on. Globular clusters is a different entity altogether. They are the oldest and very massive and very dense objects, and they are believed. So the formation of globular clusters is that they are small galaxies which have been captured by the Milky Way. This has also been explored because we are seeing some stellar what do you say, the composition of stars such that it cannot be just by stars which are formed at the same time from one molecular cloud, this way we say from open cluster. So based on the stellar content, that means based on the stars that we see in globular clusters, particularly in some of the cases, large clusters, we think that their formation mechanism is kind of different. And one of the methods could have been that they are small galaxies which are captured by Milky Way, which is a relatively large galaxy. So open clusters do not lead to the formation of globular clusters. Open clusters, even in the beginning stage, they have much less mass or very less number of stars, so it cannot evolve to a globular cluster.
Ma'am, how does the study of clusters help us unravel the mysteries of the early universe?
So globular clusters, because if you are studying open clusters, that is local. That means we are seeing in the past million years. But if you want to understand about the early universe, true clusters, globular clusters are what you should look at, because they formed very early on in time. Okay, but then you can't just look at the globular clusters in our galaxy, because that is very local to us. So if you're really wondering about clusters for early universe, one has to study them from many different galaxies. People do try to study globular clusters and globular cluster population and try to see how many globular clusters formed, what was the nature of the stars in these globular clusters, and based on this they try to estimate about when these would have formed, but till date we do not have very clear answers to this. So there are lots and lots and lots of open questions which are still there in every sphere, and people are really, astrophysicists are really rushing and trying to find answers to them with larger and better instruments, the IIST and many, which is one of the most recent ones to be launched, which is very large in size. We hope to be able to answer some of these questions.
So, ma'am, I'm going to the last question. It's from Hari Govind. He's studying in 12th. Stellar black holes are considered to be the dead remains of massive stars. Before ending up to a black hole, the star will undergo a supernova. All the mass pulling to its center due to self gravity and release of so much energy in the form of a supernova. Could it be a reason why the black hole has high gravity? Do decreasing in energy may make increase in gravity?
Because of its compact shape. Okay, all of you must have come across this concept of escape velocity, right? So escape velocity, is just related to the mass and the radius, isn't it? You know the escape velocity of Earth, and you know how to calculate it. So, square root. So if you square root, and if you put the radius, so mass and radius combination, you can get escape velocity. So you Earth mass, you can calculate escape velocity becomes the velocity of light. And you will see that it has to be really small in size. So any object has to first compactify. For it to become a black hole, information should be able to escape, which is light in this sense, which means the escape velocity should be the velocity of light. So in the case of supernova black holes, what happens is the matter, the core that is remaining after the outer layers are have exploded, because of the shocks and so on, the core that is remaining is so massive, and there is no more nuclear reaction that can hold it up. So it just collapses on itself, and it's such a compact shape that it leads to the formation of black hole. But the thing is inside the black hole. All we know that there is some body since light cannot escape, I do not know what is inside it. What is the shape of the core inside the black hole? There's no way we can know, because there is a certain radius from which light can no longer escape. Okay. So I hope this to some extent helps answer this.
Ma'am, Adil Pradesh have one more doubt. Is there any green stars, and can we see them?
Okay, as I mentioned, the reason why we don't see green stars is these stars. See, we see what do you say, certain objects of a certain color, because they are that light is prominently reflected from that surface. Correct. That's why we see certain objects to have certain colors. But when we are seeing stars, they have a range of wavelengths which they are giving out. That is known as black body radiation. I'm sure all of you are familiar with that concept. That's why I'm not going into it. But I would say that certain wavelengths, this is a continuum radiation where the peak at certain wavelength is the highest, because of which if it is peaking, which we can see, if it is peaking, which we can see it as blush, but if it is peaking also, it's such that reception of eye is such that it sees all these colors together, and therefore it appears to us greenish and so on, but it doesn't really appear greenish, because for it to part should be much higher than bluish and reddish, which is not the case for black body radiation. It's a continuum radiation. Okay, so all I will say, if you are not familiar with these concepts, is that the fact that it's a black body radiation plus the fact that our eye, the rods and cones which are present in our eye, they do not allow us to see, even though the emission, the black body radiation, our eye cannot see that as greenish. We see that as a combination of green and red and neighboring colors, and we see it yellowish. In fact, even for the sun, the black body is in green, but we see it as yellowish. Okay. So it is just this combination of these two. That's why we don't see greenish stars. You will rather see blue stars or yellowish stars. Okay.
So I guess it's time to wind up our Q&A session. Thank you all.
Yes, thank you.
Thank you. Thank you, teacher.
Good evening, everyone. I'm Dwayne. I'm studying in 9th standard. So I'm so thankful for giving me an opportunity to deliver my vote of thanks in the 68th webinar session Star Clusters, Jewels in the Sky. It was a wonderful session with Sarita ma'am. The class was absolutely amazing, interesting, and mind blowing. Hope it inspires the young minds present here. So, you are also a great inspiration, ma'am. So, first of all, let me thank our special guest and speaker of our webinar session, Dr. Sarita ma'am. And I express my sincere gratitude to all the distinguished personalities for their valuable presence and constant guidance. Let me thank Navani Detan and Eleonora for their actions. Finally, let me express my thankfulness to all the attendees who had made this webinar wonderful. So before concluding, a slight reminder for students: don't forget to check out the link for quiz that have been posted in the comment section. So let me conclude it. Have a nice day. Thank you.
Yes. Thank you. All right. Bye, everybody.
Thank you very much. It's an exciting time for our students. Although their numbers are small, but they are